Have you ever noticed how a football changes speed the moment it's kicked? Or how a moving car comes to a halt when brakes are applied? Behind these everyday events lies one powerful physics idea: the rate of change of momentum. When a force acts on a moving body, it causes a change in velocity. And with that change in velocity comes a change in momentum. This forms the basis of how we define and measure the effect of force in physics. Momentum, you may recall, is the product of mass and velocity. So, if either of these changes, momentum changes. But what's even more interesting is how fast that change happens. That's what we call the rate of change of momentum. And it is this rate that tells us the impact or influence of force. Let's dig deeper into how we derived this idea and where it leads us. Let's now understand this with a basic setup. Imagine a body of mass m is acted upon by a force for some time t. Its velocity changes from an initial value u to a final value v. Now, momentum is mass into velocity. So initially, the momentum is mass m multiplied by initial velocity u, which is m into u. Finally, it becomes m into v. The change in momentum is final minus initial, that is m into v minus m into u. This simplifies to m into open bracket v minus u close bracket. Now, when we divide this change in momentum by the time interval t, we get the rate of change of momentum. That is m into open bracket v minus u close bracket divided by t. Hold on, this looks familiar, doesn't it? Because v minus u divided by t is the formula for acceleration. So, this becomes m into a. And there you have it, the rate of change of momentum equals mass into acceleration. This expression, rate of change of momentum equals mass into acceleration, is no ordinary result. It's actually the mathematical form of Newton's second law of motion. It tells us that the force applied on a body is equal to its mass multiplied by the acceleration it experiences. So, force equals m into a, where m is mass in kilograms and a is acceleration in meters per second squared. This relationship is central to all dynamics. Whether we are launching rockets, designing roller coasters, or programming car safety systems, we use this same law.
But let's not keep it in formulas alone, let's bring it to life. Think about a cricket ball versus a table tennis ball. If both are hit with the same bat, which one hurts more? The cricket ball, because its mass is greater, and hence its change in momentum is higher. Or consider a rocket engine. The large change in momentum it produces is due to both the speed and mass of exhaust gases. That's how it lifts tons of payload into space. And here's a life-saving example: airbags in cars. When a car crashes, the airbag inflates to slow the passenger down gradually. This increases the time over which momentum changes, which reduces the force experienced by the person. That's physics saving lives in motion.
Let's look at this from a slightly different angle using calculus notation. Say we observe the change in momentum over a small interval of time, which we call delta t. Momentum at any moment is mass into velocity, that is p equals m into v. The change in momentum is written as delta p, and when we divide that by delta t, we get delta p divided by delta t. Now, assuming mass stays constant, we can write delta p as mass into delta v. So the expression becomes mass into delta v divided by delta t. But what's delta v by delta t? That's acceleration again. So once more, we arrive at rate of change of momentum equals mass into acceleration. Two different paths, one powerful truth.
So let's wrap this up. The rate of change of momentum is the measure of how quickly an object's motion changes when a force is applied. We derived it using the idea of initial and final momentum, and then again using small time intervals. Both give us the same result. Force equals mass into acceleration. This principle is not just mathematical, it's physical. It helps us design vehicles, build safe systems, and understand motion around us. I hope now you see how deeply connected momentum and force are, from a bouncing ball to a flying jet. In our next session, we'll explore how this law leads into even broader principles like impulse and conservation of momentum. Until then, keep questioning, keep exploring physics,